What looks like a stunt from a sci-fi movie was actually the only way Curiosity could survive Mars, and the reason is hidden in a problem no parachute, no wheels, and no ordinary landing gear could solve. NASA did not choose the sky crane because it was elegant. It chose it because every easier-looking option broke one of three requirements: land close enough to a mountain inside Gale Crater, deliver a rover almost the mass of a small car, and put that rover directly onto its wheels, undamaged, with no landing platform trapping it, no airbags bouncing it, and no rocket exhaust sandblasting it. Curiosity's landing was not one clever trick. It was a chain of rejected alternatives. Each rejection came from Mars itself. The planet has just enough atmosphere to burn you, but not enough to stop you. It has gravity strong enough to make impacts deadly, but air too thin for parachutes to finish the job. It has dust, rocks, slopes, and communication delays so long that no human can steer the last moments. By the time engineers reached the final design, the sky crane was less like a wild idea and more like the last remaining square on a very small chessboard. Start with the simplest wish. Put a rover on Mars the way you might unload equipment from a truck. Land a platform, drive down a ramp, begin the mission. That is close to how earlier missions worked. Viking in the 1970s used heat shields, parachutes, and rocket-powered landers with legs. Pathfinder in 1997 carried the tiny Sojourner rover inside a cluster of airbags. Spirit and Opportunity used the same general airbag idea in 2004. They hit Mars like padded packages, bounced, rolled, deflated, opened pedals, and the rovers drove away. For small spacecraft, this looks almost forgiving. Pathfinder's rover was only about 11 kilograms. Spirit and Opportunity were about 185 kilograms each. Curiosity was about 899 kilograms, roughly the mass of a compact car. The entire entry, descent, and landing system was more than 3 metric tons when it hit the top of the Martian atmosphere. Scaling an airbag system from a 185 kilogram rover to an 899 kilogram rover is not like making a backpack a little larger. It is like deciding that because a bicycle helmet protects a cyclist, a building-sized helmet should protect a moving truck. The forces grow, the materials grow, the gas volume grows, and the landing becomes a giant uncontrolled bounce with a delicate robot inside. Airbags also need tolerance for wherever they stop. A small rover can afford to sit on top of a folded lander for a while, unfold itself, and carefully roll down a ramp. Curiosity was too large for that architecture. It carried a drill, cameras on a mast, chemistry instruments, a robotic arm, and wheels built for crossing kilometers of crater floor. Landing it inside a cocoon, then asking it to escape a platform on an uneven Martian slope, added a new failure mode at the exact moment the mission needed to become simple. So airbags failed the weight requirement, and a platform failed the put the rover straight onto the ground requirement.
Then try a more grown-up method. Use landing legs and rockets, like Viking. Come down vertically, throttle the engines, touch down softly. For a stationary lander, that can work. For a rover the size of Curiosity, it creates a different trap. If the engines stay attached to a landing platform above or around the rover must later get off that platform. The ramps must work. The platform must sit level enough. The rover must not be blocked by rocks. A single bad tilt could turn a billion-dollar mobile laboratory into a very expensive object on a porch. If the engines are attached directly to the rover, the problem gets uglier. Rocket engines firing close to the surface do not gently blow dust aside. They excavate. They kick stones. They can dig holes under the vehicle, create unstable touchdown conditions, and throw high-speed grit into instruments, lenses, joints, and wheels. Curiosity needed to arrive ready to drive and sample, not coated in debris blasted up by its own descent system. Landing legs also sound simple, until the vehicle becomes large. A legged lander must absorb the touchdown energy, stay stable on slopes, avoid rocks, and keep the body from tipping. The wider the stance, the heavier the structure. The higher the rover sits,
the more elaborate the deployment. Curiosity was already carrying an enormous science payload and a radioisotope power system. Every kilogram spent on giant disposable legs was a kilogram not spent on science, strength, or fuel. The first trade-off was clear. Airbags were too violent at this mass. A lander platform added escape risks. Direct rocket landing threatened the rover with its own plume. Legs added weight and geometry problems. The landing system had to slow the rover with rockets, but keep the rockets away from the ground. It had to avoid a platform, but still place the rover gently on the surface. That contradiction is the seed of the sky crane. But before any of that mattered, Curiosity had to survive the atmosphere. Mars is awkward because it sits between two easier worlds. If Mars had no atmosphere, landing would be a pure rocket problem, like touching down on the moon. Hard, but clean. If Mars had a thick atmosphere, like Earth's, a parachute or wings could do most of the work. Mars has the inconvenient middle case. Its atmosphere at the surface is usually less than 1% of Earth's sea level pressure. But at interplanetary speed, even that thin air becomes a wall. Curiosity arrived at roughly 5.9 kilometers per second. That is more than 21,000 kilometers per hour. At that speed, the spacecraft does not simply rub against air. It compresses the gas in front of it so violently that the gas heats to extreme temperatures. The heat shield's job is not to stay cool. It is to sacrifice itself in a controlled way, carrying heat away as material chars and ablates.
The heat shield was about 4.5 meters wide, one of the largest ever sent to another planet. Its blunt shape created drag and slowed the vehicle dramatically. This first phase removed most of the incoming energy, but most is doing heavy work here. After the fiery entry, the spacecraft was still moving hundreds of meters per second, far too fast to land. This is where Mars refuses to cooperate. A parachute can open only after the vehicle has slowed enough that it will not shred the fabric instantly. But once the parachute opens, the thin air limits how much drag it can produce. Curiosity's parachute was about 21.5 meters across, a supersonic disk gap band design, deployed at around Mach 1.7. It was the largest supersonic parachute NASA had flown on another planet at the time. And it still could not land the rover. That sentence is the heart of the problem. The parachute was not a landing system. It was a speed reducer. It brought the spacecraft down from deadly fast to merely impossible. In Earth air, a parachute that size feels enormous. In Martian air, it is a temporary hand on the shoulder. Useful, essential, but not enough. There was also a precision problem. Curiosity was not aiming for a generic flat plane. It was going to Gale Crater, near Mount Sharp, a layered mountain about 5 kilometers high. Scientists wanted those layers because they recorded changing Martian environments. But the landing zone had hazards nearby: crater walls, rough terrain, dunes, and slopes. Earlier Mars landings had huge uncertainty ellipses. Curiosity needed a much tighter target, about 20 by 7 kilometers, far more precise than the broad landing footprints of earlier rover missions. During entry, Curiosity did something more sophisticated than falling behind a heat shield. It used a guided entry. Small masses were ejected to shift the center of gravity, giving the capsule a little lift. Not airplane lift, but enough to steer through the upper atmosphere by banking. The spacecraft could correct for atmospheric variations and aim itself toward the landing ellipse. This helped with precision, but it also made the landing sequence more interdependent. The heat shield, parachute, radar, rockets, and crane all had to hand control from one phase to the next. No single device could be trusted to do everything. Imagine trying to stop a piano dropped from an airplane, but the piano must land upright on its own casters inside a small parking space without scratching the floor, and the room has air so thin that a parachute works only halfway. That is closer to Curiosity's landing problem than the usual phrase "soft land" suggests.
time the parachute had done what it could, Curiosity was hanging inside its back shell below a huge canopy, descending towards Mars. The heat shield had separated, exposing the rover and the descent radar. The radar needed to measure altitude and velocity. It had to know when the atmosphere phase was over, and the powered phase had to begin.
At about 1.8 kilometers above the surface, the parachute and back shell were no longer enough. The descent stage separated. 8 throttleable rocket engines fired. The rover, still folded beneath this powered platform, was now committed to the most delicate part of the sequence. This powered descent stage is easy to misunderstand. It was not a helicopter. It was not hovering around with plenty of spare time. It was a rocket platform burning fuel in a narrow window, slowing from roughly 80 meters per second toward a near hover. If it started too high, it wasted fuel. Too low, it ran out of time. Too much sideways motion and touchdown became dangerous. Too much dust or plume interaction near the ground and the rover could be damaged. A normal answer would be keep descending on rockets until the rover lands, but that brings the rocket plumes too close to the surface. Another normal answer would be land the powered stage on legs, then lower a ramp, but that brings back the platform problem. The engineering solution was to split the last seconds into 2 vehicles, the thing that flies and the thing that lands. At roughly 20 meters above the ground, the descent stage began the sky crane maneuver. Curiosity was lowered on 3 nylon bridles, plus an electrical umbilical, to about 7.6 meters below the rocket platform. The rockets stayed high enough that their exhaust was less destructive at the surface. The rover hung low enough to touch down directly on its wheels. This is the part that looked theatrical. A hovering rocket lowering a car-sized robot on cables feels like something built to impress an audience. But mechanically, it solved several problems at once. First, it made the rover its own landing gear. Curiosity's wheels and suspension were already designed to carry it across Mars. The rocker-bogie system could handle uneven ground and distribute loads. Instead of carrying a separate landing platform with legs, NASA used the rover's existing mobility system for the final contact. Second, it kept the descent engines away from the soil. Not infinitely far, but far enough to reduce direct plume damage. The rover did not have to pass through a storm of debris created inches below its belly. Third, it removed the need for ramps, pedals, or drive-off event. The moment the wheels sensed touchdown and the load on the cables dropped, the rover could cut the bridles. The descent stage would fly away and crash at a safe distance. The rover would already be on Mars, in driving configuration. The cables were not an afterthought. They were part of the control system. A hanging rover can swing, twist, or feedback motion into the platform above it. The descent stage had to manage that pendulum while throttling engines and descending. The rover had to deploy its wheels before touchdown, sense contact correctly, and sever the connection without dragging anything across itself.
This is why untested needs careful meaning. The complete sky crane could not be tested on Earth in full Mars conditions. Earth's gravity is stronger. Earth's atmosphere is thicker. A full-scale powered descent with a suspended rover would not reproduce the same dynamics without enormous complications. But its parts were tested relentlessly. Engines were tested. Radar was tested. Parachute materials were tested in extreme conditions. Software was simulated. Cable cutters, bridles, sensors, pyrotechnic devices, and deployment mechanisms were tested as components and in combinations. The untested thing was the complete choreography on Mars. That choreography became famous as the 7 minutes of terror. The phrase was not marketing exaggeration. From the top of the atmosphere to touchdown took about 7 minutes. Radio signals from Mars took about 14 minutes to reach Earth that night. By the time controllers received confirmation that entry had begun, Curiosity had already either landed safely or crashed. There was no joystick, no abort button, no human correction. The spacecraft was executing a script written years earlier, using sensors and software to decide when to move to the next phase. The sequence was brutally timed. Cruise stage separation, atmospheric entry, guided banking, peak heating,
peak deceleration, parachute deploy, heat shield separation, radar lock, backshell separation, powered descent, sky crane lowering, touchdown detection, bridle cut, flyaway. Each event had to happen after the previous one succeeded, but before physics closed the window. The heat shield had to come off so the radar could see the ground. The radar had to work so the descent stage knew its altitude. The parachute had to slow the spacecraft, but then get out of the way before rockets fired into the backshell. The descent stage had to lower the rover, but not land on it. The rover had to cut itself free, while the rocket stage still had enough control to divert away. On August 6, 2012 UTC, the signals came back one by one. Then came the line that mattered. Touchdown confirmed. Curiosity had landed in Gale Crater, within its target ellipse, standing on its 6 wheels. The sky crane had worked the first time it was ever used on another world. Its success did not make the design less strange. It made the strangeness easier to understand. It proved that for large Mars rovers, landing directly on wheels was not reckless. It was a clean architecture. The dangerous hardware, the fuel tanks, the rocket engines, the landing structure, all disappeared from the rover at the moment they were no longer needed. Nothing had to unfold into a ramp. Nothing had to be driven off. Nothing had to remain as a lander piece. This changed the design language of Mars missions. Before Curiosity, each rover landing seemed to belong to a different era of improvisation. Airbags for small rovers, legged landers for stationary science, platforms and pedals and ramps. After Curiosity, the sky crane became the proven answer for heavy mobile laboratories.
Perseverance used the same basic architecture in 2021, but with upgrades. It was even heavier, about 1,025 kilograms. It carried sample caching hardware and delivered the Ingenuity helicopter. Its landing system added terrain relative navigation, comparing camera images during descent with onboard maps to avoid hazards and choose a safer spot. The landing ellipse became smaller, and the target, Jezero Crater, was more hazardous and scientifically richer. The sky crane was no longer the shocking new idea. It was the trusted final step. That is the quiet legacy of Curiosity. It did not just land a rover. It separated the Mars landing problem into pieces that could each do what they were best at. The heat shield handled hypersonic energy. The guided entry handled aiming. The parachute handled the middle speed range. Rockets handled the speed the parachute could not remove. The crane solved the last meters, where rocket exhaust, landing legs, and rover deployment all became liabilities. The apparent stunt was really an accounting trick against physics. Mars forced NASA to spend mass, fuel, time, and risk carefully. Airbags spent too much on impact survival. A platform spent too much on post-landing escape. Direct rockets spent too much risk near the soil. Heavy legs spent too much mass. The sky crane spent complexity instead. It accepted a difficult sequence in exchange for a rover placed gently, precisely, and immediately on its wheels. That trade-off is not automatically right for every mission. A small probe might use airbags. A stationary lander might use legs. A future human lander will need something larger and stranger again, because a crewed Mars vehicle could be tens of tons, far beyond Curiosity's scale. But Curiosity showed that when the payload becomes a heavy rover, Mars leaves a narrow path through the design space. Not the simplest path on paper, the simplest path that still works. So the sky crane was never a circus act suspended over another planet. It was the answer to 3 incompatible demands: land accurately, land heavy, and let the rover survive as a rover, not as cargo trapped inside its own landing machine. If you were designing the next jump in Mars landing technology, which constraint would you attack first? A much stronger supersonic parachute? Cleaner rocket plumes near the ground? Or a completely different way to slow down heavy payloads before they ever reach the surface?